All right, so this video is going to start the new waves unit. We're going to go over pages 1 through 3 in this video. So starting off, we're going to talk about energy transfer. So this is probably things that you learned a while back. We're going to go over the 3 types of energy transfer. First one is going to be conduction. That is the transfer of energy by contact. So key thing there is contact between objects. So what's happening is energy is going from atom to atom or molecule to molecule through that contact. Okay, so certain materials are better conductors. Okay, so like things like metal versus wood. Okay, so certain materials are better conductors. Okay, so think of like in the microwave, if you put like a plastic bowl in there and heat it up versus like a glass bowl, okay, and you reach in to grab it, more than likely you're going to burn yourself on the glass bowl because that glass is a better conductor, it absorbs heat, and it's able to transfer heat as well. Okay, so an example would be something like ironing a shirt, okay, or touching a stove. Okay, those are all instances where heat or energy is transferred through touch. Okay, then you have number 2 is convection. That is a transfer of energy through movement of a liquid or gas. Gas in this case can be air. Okay, so that's technically what the air we breathe is, gas. Okay, it's made up of different gases like oxygen, nitrogen, all those. So key thing here is we're looking for via currents. So that means it's basically directional. Okay, so you got to think about which way is currents flowing. Okay, so usually heat rises. So a lot of our examples are things like a hot air balloon, okay, where you heat up the air. You heat up the air and it goes up into the balloon and fills the balloon with hot air. Okay, or you have something like roasting a marshmallow. Okay, so what happens is at a fire, what's happening is the fire is heating up the air particles and the air particles are rising above the fire. So that's why it's hot whenever you put your hand above a fire. Okay, so it's very directional, usually meaning it's going to go whichever way the current is going. So in this case, the air is going up. Okay, now you can also look at things like boiling water. Okay, so that is where hot water rises to the top and cold air goes back down. Cold water goes back down, and then that cold water becomes hot and rises to the top, and then it goes back down. When the cool water goes back down. Okay, so those are all instances where it's very directional. It's through a current. Okay, now the only thing that usually doesn't go up is one example we talked about was like a blow dryer for hair. Okay, that would be an example of convection as well. It's just going to go whichever way you're pointing the hair dryer. Okay, then you have radiation. Radiation is a transfer of energy through electromagnetic waves. Okay, so this one is all directions. Okay, so convection was very directional because it was based off currents. Okay, so on radiation, it just goes all different directions. So if you have something like the sun, okay, you've got radiation going this way, you've got this way, you've got this way, you've got this way. It's basically going all around. It's not just one direction. Okay, or things like a microwave. A microwave just generally heats the whole area. It's not pointed at one certain area. It's just microwaving everything that's in the microwave. Or you have something like fire. Okay, so fire is emitting radiation. So if you sit around a fire, okay, so say you have like 6 chairs around a fire, that fire, is emitting energy in all directions. Okay, the one thing that can get confusing is the whole marshmallow thing here and versus radiation. Now, if you hold a marshmallow above a fire, is it going to get radiation? Yes. Okay, because radiation is basically energy is being radiated away from the fire. Okay, so like when you sit in your chair, you're feeling that heat. It's not necessarily from the convection of the fire, it's from the radiation of the fire. So that energy that's in the light, okay, is emitting outwards towards you sitting in the chair. But when you put that marshmallow over the fire, now it's mostly convection. That's what makes it burn a lot quicker is that heat that's coming from that. So radiation is basically heat that's not really in a current. Okay, it's basically all around. So like if you put your hand like around a stove, okay, it's going to emit heat no matter where you put your hand. Okay, so if I put my hand on the right side of the stove versus the left side of the stove, you're both going to feel that heat in both directions because of that radiation. So those are your 3 types of energy transfer. Now, a wave, which we're going to talk about a lot in this unit, a wave is a transfer of energy in the form of a disturbance through a medium. Okay, medium just means something to go through. It can be material. Material means actual physically you can touch it, or in this case, space. Okay, so space is technically not a material. There's nothing there. It's a vacuum. It's still considered a medium since waves are going through it. Okay, but it is not considered material. You can't touch it. Okay, so waves transfer energy but not matter. Okay, so that means a particle is not going to start here. Okay, so say this particle is here. It's not going to just go through the wave here and then it ends up here. What happens is it transfers energy to the next particle next to it, and then that particle transfers energy to the particle next to it. It's kind of like a game of telephone. Okay, your original particle is still back at the beginning. But all waves require a source of energy, so you need something to get it going. Now, waves can be classified in two categories: electromagnetic waves and mechanical waves. Okay, electromagnetic are waves which we do not require material medium, so things that can travel through space just fine. That means it doesn't need air, doesn't need water, doesn't need a rope, anything like that. Now, mechanical waves, which are something that do require a medium. Okay, so a material medium, like something physical that you can touch. Okay, so like if you send a wave down on a rope, that would be a mechanical wave. Okay, if you have a wave like in a pool, that would be a mechanical wave. Now, electromagnetic waves, so we're going to go back to chemistry a little bit. Okay, so remember we had a saying that was red Martians invade Venus using X-ray guns. So hopefully you remember this from chemistry. These are your EMR, your electromagnetic waves. These are the things that can travel through space just fine. They don't actually need a material medium. So remember, R was radio. That was our very low frequency, long wavelength, so very low energy. Then M was your microwaves. I was your infrared. Okay, Venus is visible light. Okay, so that's the visible light you can see. So that would be your Roy G. Biv. Okay, U would be your UV. Okay, then X-ray is going to be X-rays. That one's not too hard. And then G is going to be your gamma. Okay, so these are all electromagnetic waves. So if you can remember that, it's going to be pretty easy to distinguish between the two. So if I ask you, like in this table here, if I were to ask you, write down which one's which, electromagnetic or mechanical, if you know that EMR list, it's going to be pretty easy. Okay, if it's not on that list, that means it's mechanical. So water, okay, that is going to be mechanical. It needs water. It needs a material medium. Light, that's on my EMR list. Okay, so that is electromagnetic. Infrared, that's on my list. Sound is mechanical. Okay, one, it's not on my list, and two, sound needs air particles to transfer energy. Okay, so like sound cannot travel through space. So whenever you see movies where things explode in space, you actually would not hear it in space. You'd see it, but you wouldn't hear it. Okay, so X-rays, okay, that is going to be your electromagnetic. Radio, that's going to be electromagnetic as well. A wave and a rope, so it has a material, so that is mechanical. UV is electromagnetic. Wave and a spring is a material, so that's mechanical. And then gamma rays, that's going to be electromagnetic. Okay, moving on to the next page is a source of energy will produce a wave pulse. Okay, so a pulse is a single wave disturbance. Okay, so I'm seeing a lot of students that are getting kind of hung up on when I ask, what is a wave? They're like, well, it's a pulse. Well, a pulse creates that disturbance, but the wave is actually from the pulse. Okay, and it's just the transfer of energy through that medium. Okay, so the pulse just makes it start. Okay, so if the source of energy periodically produces pulses, a continuous wave is formed. So that means if you just keep repeating the same pulse, okay, what you're going to do is you're just going to create a continuous wave where it's just going to keep going and going. Okay, so don't get too hung up on that. The pulse is just something that gets that wave going. Now, there are three types of mechanical waves. So something that requires a medium is your first type is a transverse wave. Okay, so a transverse wave is the kind of wave that if I asked you to picture it in your mind, okay, you typically see something that goes up and down, up and down. That's a transverse wave. So what makes a transverse wave is displacement of the medium is perpendicular to the direction of the wave. So I think we can agree is if you're if you're holding this rope and you're sending pulses down, the direction of the wave is heading towards the wall. Okay, so that would be your direction right there. Now, if I had like a little object that was attached to that string, okay, if I asked you, what is that object going to do as the wave moves across it? Okay, the object's not going to keep going down and down and down and end up at the wall. It's not going to do that. What's going to happen is the object's just going to sit there and go up and down, up and down, up and down, up and down. So it's not going to move horizontally. It's just going to move vertically. So that means its displacement is going this way. Okay, so at one point it could be at the bottom. At one point it could be in the middle. It could be at the top. But the point is its displacement is vertical. Okay, and its direction, the direction of the wave is going horizontally. So that's what we mean by perpendicular. So that is a transverse wave. An example would be like waves in a piano or guitar string. If you ever pluck a guitar string and see a video in slow-mo, that's what it looks like going down the fret. Now, number 2 is a longitudinal or compressional wave. Okay, whichever way you want to remember it. Okay, longitudinal I think of as longitudinal is basically just sticking that way. It's just going horizontally. Now, the displacement of the medium is parallel to the direction of the wave. That means if I had an object on this spring, okay, let's just say it's right there, that means the direction of the wave is going back and forth this way. So direction is going horizontal. And your displacement, what's going to happen is that object's going to go back and forth, so your displacement is also in that same direction. So that means that they are parallel to each other. Now, there are a couple terms you need to know as far as a longitudinal wave goes. First is when those waves get real tight with each other, that's called a compression. That one's pretty easy to know. Okay, the term you're probably not used to hearing or saying is rarefaction. Okay, rarefaction is basically when that wave stretches out, okay, which is the opposite of compression. So the reason why I started is you will need to know that. If I ask you to label a compression and a rarefaction on a longitudinal wave, okay, you would have to be able to use that rarefaction. You need to understand what that word means. Okay, examples would be like waves in deep water, which we'll look at here in just a second, and sound waves. Sound waves are actually compressional. I mean, they just go back and forth, side to side. Okay, your third type is called a surface wave. A surface wave is both transverse and longitudinal. Okay, so just adds up both of them. So if you were to look at the surface is doing this. Okay, up and down. So that means it looks like it's a transverse wave. So that's why it's transverse. But if you think about what's happening with water is it's stretching and compressing up and down as well. Okay, at one point you have water that's higher, and at one point you have water that's lower on the surface. That means it's got to be compressing and stretching. So that means it's both transverse and longitudinal. Okay, so those are your 3 types of mechanical waves. Now, our summary that we're going to do is we're going to talk about just basically what we already went over. Okay, so waves, and we're going to break those into 2 categories. So waves were broken into 2 categories. You had electromagnetic and you had mechanical. Okay, electromagnetic, okay, no medium is needed. That means it can travel through space. It does not need a material. Okay, now mechanical, it does need a material medium. Okay, it needs something. It needs like something tangible that you can touch. Okay, water, air, okay, a rope, a chain, anything like that, a slinky. Okay, that would be an example of a mechanical wave. Now, your EM, remember, if you can remember the red Martians invade Venus using X-ray guns, those are your electromagnetic waves. Okay, then that makes your life a lot easier. Now, those are all considered transverse. Okay, electromagnetic waves all look like this. Because you got to think about is transverse waves, okay, versus longitudinal or compressional is when it's traveling through space, there's nothing really to compress. Okay, so that means it's purely transverse, which is just your typical looking wave. Now your mechanical wave, okay, is broken into 3 different categories. You had one which was transverse, which we just talked about, so it could be that. Okay, or it could be your longitudinal or compressional, whichever way you want to say it. Okay, going side to side, or it could be a surface wave, okay, which is both. Okay, so that will end that video. The next few pages, we're going to put that into practice and do some practice.